My name is Azim bin Azman.
My name is No Amirul Mini.
I'm one Adrian Jamil.
Alright, and my name is Muhammad Maharis.
Alright, good day. We are Group 3 and today we present our case study on enhancing safety and sustainability awareness in workshop practice, focusing on the milling workshop at the Faculty of Mechanical Engineering. We chose the milling workshop because it is one of the most highest risk and resource consumption environments in our engineering training. Milling involves rotating cutting tools, high-speed spindles, metal chips, cooling systems, and continuous power consumption, making it an ideal case for examining both occupational safety and environmental responsibility side by side. Our case study has 4 specific objectives. Number 1 is to assess current safety practices in the milling workshop and determine whether they are adequately protecting students and staff from mechanical, chemical, and ergonomic hazards. Number 2, to evaluate existing sustainability practices, particularly coolant management, scrap metal handling, and energy use against the principle of SDG 12, responsible consumption and protection. And number 3, to identify gaps between our current practices and legal requirements set out in the Factories Machining Act 1967 and to understand the consequences of non-compliance. And finally, to propose realistic, cost-aware solutions that improve both safety performance and environmental sustainability while building safety and sustainability awareness as a core engineering competency.
Let's take a look at what safety procedures we have to follow in our lab. Firstly, students must wear PPE, which was our faculty jacket, so that we can avoid from any flying metal chips, so that we don't get injured when we are doing our work. Secondly, is to wear our safety footwear, which was here. It's my safety boots. Yeah. The third one, we have to wear safety goggles, so that any flying metal chips cannot enter our eye and injure us. And the last one is, of course, no smoking. Safety and sustainability are critical here because milling is unforgiving of carelessness. A single mistake here can lead to injury, which could result in permanent disabilities. Technicians or responsibility extends beyond producing accurate parts. It includes protecting people and resources.
Milling machine is fitted with an accessible emergency stop button, and the workshop maintains a visible evacuation route and fire extinguisher placement. Staff conduct a basic safety briefing before any new student operate a machine independently. On the sustainability side, cutting coolant is circulated through the machine built-in reservoir rather than being discarded after every session. Reducing fluid waste, metal swab, and off-cut are collected in designated scrap bins for recycling rather than general waste disposal.
Machines are powered down between scheduled sessions rather than left idling. Overhead lighting has been partially upgraded to LED features in sections of the workshop, reducing electricity consumption. These 5 practices show that the workshop has a reasonable safety and sustainability foundation. However, investigation found that implementation is inconsistent and several gaps remain, which we'll discuss next. The 4 major issues spanning technical, safety, and accessibility dimensions. First issue is persistent machine maintenance and calibration. Several milling machines show that sign of delayed maintenance, vibration during operation, dull cutting tool left in use beyond their service life, and inconsistent calibration checks. This caused a lack of a formal preventive maintenance schedule and limited technician staffing relative to machine count. Impact: poor dimensional accuracy affects student learning outcomes. Increased scrap rate and critically uncalibrated or worn tooling increase the risk of tool breakage, which can eject metal fragments at high velocity, a direct safety hazard.
Alright, and the second issue is inhalation of coolant mist and metal fume exposure. During high-speed milling, coolant mist becomes airborne and ventilation in the workshop is limited to natural airflow and a few ceiling fans, rather than a dedicated local exhaust ventilation. This is caused by an absence of engineered ventilation and extraction system, a reliance on PPE alone rather than engineering controls hierarchy, Repeated exposure to mineral oil mist is linked to respiratory irritation, and prolonged exposure, occupational asthma, and dermatitis on contact. Students and staff working multiple consecutive sessions face cumulative exposure risk. Poor air quality also lowers concentration, indirectly increasing operator error.
Now we move into the third issue, excessive scrap metal and coolant wastage, sustainability. Despite recycling effort, scrap generation remains high due to the trial and error cutting by inexperienced students, and coolant is sometimes topped up or fully replaced rather than filtered and reused due to the contamination from swath setting in the reservoir. Cause the no formal waste segregation protocol distinguishing and recycle swath grade no coolant filtration. The cause is no formal waste segregation protocol distinguishing recyclable swath grades, no coolant filtration or skimming system to extend fluid's life. Now, the impact is increased raw materials consumption, contradict SDG 12, resource efficiency goals. Contaminated coolant disposed improperly can contaminate soil or water if not handled as scheduled, based on the Malaysian environmental regulation.
Issue 4, poor ergonomics and manual handling. Workpieces and vices are frequently lifted and positioned manually without lifting aids, and machine operating heights are not adjustable for different student statures. This caused by the workshop layout, which was not ergonomically reviewed since installation. Budget has not prioritized lifting equipment for a teaching lab. This will cause risk of leg injuries. This will this caused by the cumulative injury from repeated improper lifting throughout the whole semesters that the students are experiencing. An occupational health issue, OSHA 1994, explicitly requires employers and by extension institutions to mitigate.
For each issue, we propose a solution grounded in a specific code of or standard. For the first issue, preventive maintenance schedule. So it is address issue 1. Local exhaust ventilation and mist collector addresses issue 2. And coolant filtration system and swath segregation address issue 3. Ergonomic station review and lifting aid addresses issue 4. So each solution is deliberately chosen to be implementable within a teaching workshop budget, not theoretical best practice disconnect from the reality. So,
Now, none of this comes free. Ventilation systems, coolant filtration, these cost money. A faculty has to justify that against a tight budget and stricter waste rules, machine downtime for maintenance. That eats into machine hours. Few hours means few students get hands-on time with each semester. So how do we balance that? By balancing risk severity first and cost second. Ventilation and machine maintenance prevent injury and chronic health damage. These are non-negotiable. Fund it first, whatever it costs. Because under the Factories and Machining Act and OSHA 1994, safety is an option, it's the legal minimum. Coolant filtration ergonomic aids are still important, but the risk there builds up over time instead of hitting immediately. Those can be phased into the budget cycles. The bottom line is that the cost decides the pace. It never decides what risk is acceptable. SDG 12 does not let students or staff absorb unmitigated hazards just because an upgrade hasn't landed yet. So to summarize, our milling workshop has a solid baseline of PPE use, signage, and emergency protocols. However, the gaps remain in maintenance consistency, ventilation, waste and coolant management, and ergonomics. Each are traceable to specific legal and environmental standards. Alright, that's all.